Good afternoon. It's a pleasure to be here during this talk. This work is a collaboration between myself, Professor Sebastian Ferr, and Professor Daniel Shears. When Professor Ferr and I were in a sabbatical leave to University of Colorado in Boulder last year. And this talk is about, we are dealing with the problem of roto-translational motion. That is a classical one. And it's a problem that in literature, when we are dealing with this, is known that it's a very complex problem because we have many variables, many degrees of freedom. It's not an analytical integrable problem. So in this work, we are trying to apply classical techniques in order to find approximations to the triaxial model and to the axisymmetric model of the roto-translational problem, in order to find models that are analytical integrable and can provide some valuable information in terms of analytical solutions of the system. The outline of this paper, of this work here, I will introduce the problem, just like I'm doing now. I will present the canonical variables that we are considering the problem. We presented the formulation, the mathematical formulation of the problem, the model, the Hamiltonian that we are comparing with. So we present the intermediary, the concept of intermediary. That is a classical one, but some people maybe don't know. That is the key for building this analytical model. And after that, the elimination of the parallax is used to build another intermediary model that we have a different characteristic, but is also analytical. And after that, using this previous topic, we presented the roto-orbital intermediaries that we built with these two previous concepts. And after, I will show some numerical experiments that we have and the conclusion. The idea of the roto-translational motion is part of the full two-bar problem, where we consider both the orbital and the rotational motion of two bodies interacting with each other. This is very complex, so we can just integrate it in terms of numerical propagations, but if we consider some techniques, we can maybe try to find for analytical studies that are able to approach this problem. And on doing that, we need to make simplifications, but with some precision in a range that we can find valuable information about that. Usually, some people consider this kind of approximation, and you consider the central body as spherical, and you have the rigid body here, and in fact, you see how this rigid body around, for example, an asteroid around the Earth will be disturbed by a gravity gradient torque, and while he's interacting with the gravitational field, this attitude motion and rotational motion will impact in his orbital motion. Another kind of a technique that is usually used is like consider the central body as a mass, just to avoid his shape and the size that he has. We are dealing with this model here. The canonical variables that we use for this problem are the Whittaker variables for the orbital motion, and we have the Introduo variables for the rotational motion. When we plug these two variables together using a procedure that was presented in 1999 by Sansaturio and Ferr, we can put these two sets of variables together and build roto-translational canonical variables that are presented here. And if you want, this is just geometry. The idea of doing that is that when we do this, the problem that is 6 freedom, the 6 degrees of freedom, we can reduce to 4 degrees of freedom by reducing the nodes. And on doing that, we approach to do something that we can do to find us analytical Hamiltonian that we can be able to be integrated analytically. These are the Hamiltonian equations, and these are the Keplerian Hamiltonian that we put together with the Euler Hamiltonian, the Hamiltonian that will provide you the information about the rotational motion. And this is the disturbing potential that we use for the problem that will give the information about the coupling of these two bodies, these two motions. And this term that we are using here is the first order approach coming from the McGooley expansion, that is the classical one. And a third simplification that we consider here is use the idea of perturbation theory, that we have a small perturbation and you have this parameter epsilon here. In classical literature, we have this Hamiltonian that is the integrable one of the system, given by the Keplerian Hamiltonian. In our problem, we consider here, we put together the other one, and regarding this potential here, we split it in two parts, V0 and V tide, and this will give some invaluable information, because this part here, we can plug it on here and build the intermediary of the problem. That is an analytical perturbed Hamiltonian that will provide an analytical solution of the system, and this term here will be the remainder of the system, the remainder Hamiltonian that will contain information that destroys the analytical integrability of the system. And when we do that, we have a final Hamiltonian in this form, and these characteristics must be integrable and non-generated. There's two works available, two PhDs, but they are students of Professor Ferr in Murcia, in Spain, and they discuss different choices for this parameter here, for this potential here, V0. On doing that, having this potential here, we can make some organization of terms, and we have these three terms of that potential. This is going to be our Hamiltonian, our roto-translational Hamiltonian. And here you can find these cosines here are given by these terms here that are a result of these transformation metrics here. And we also, in order to simplify the model, can rescale the parameters, the moments of inertia and the momenta, in order to avoid mass and just not to be sensible to initial conditions and parameters. We would like just to see the behavior of the variables in the system and avoid sensibility with numerical values for each value here. And we also can consider here a simplification that is considered the axisymmetry in the rigid body as a first good attempt to study the problem. We will try to expand it later for a triaxial case, but we need to consider, because when we do that, when we consider A equal to B, we can simplify and decrease one order of freedom of the problem here with this variable nu, that is the rotation of the body. So on doing that, we have this Hamiltonian here, that is the axisymmetric first order roto-translational perturbed Hamiltonian. And we work with this one here. On doing that, we need to build the intermediary of the problem, that is that one that I was presenting here. And we need to find this term, this potential V0 from this term here. We need to split this term. As you can see, it's cosine of square of gamma, that is given by this expression here, and we will expand. And the idea of intermediary is that we have here the whole Hamiltonian, the Hamiltonian that will describe the system. And the idea of the intermediary, you have the Hamiltonian intermediary here, and you can avoid these terms that are dependent on higher order terms of this perturbation. On doing that, we are saying that you have this phase space, and you have the origin that we're analyzing. The complete Hamiltonian will describe the whole system perfectly, but the intermediate will approach in a certain region this system. But the idea is that in this region you can find an analytical solution of the problem. That's the point. This concept, the concept of intermediary is the classical one, as I mentioned before. You can find the classical concept of intermediary in graphical and Aeschines in this work here. After that, Depri also did define in a different way this intermediary, using the term of natural intermediary, where he expanded the idea. And they have the main differences between them here is that this classical one, by graphical and Aeschines, you can build an analytical problem, analytical solution by integrating terms of elliptical functions. And you are looking for just parts of the first order approach of the full Hamiltonian. But in Depri, the concept of Depri, where he redefined this concept of where he calls natural intermediary, he's trying to not to find just some terms of that first order Hamiltonian, but he's looking to approach the whole as much as possible, the the full first order Hamiltonian of the problem. And on doing that, you are able to integrate the system and simplify it, and just integrate it in terms of trigonometric functions. So you have a very simplified quadrature of the problem. But the price you need to pay for that, you need to perform a transformation, and then the canonical transformation called elimination of the parallax. That is this one here. The elimination. Oh, sorry, I need to mention that this classical intermediary, the common intermediary, was applied to study the roto-translational motion, and this paper is submitted to a journal in the United States and is under revision yet, is under analysis. And there is also this one by Ferr and Martin Lara that applies the idea, the concept of natural intermediary to the same problem. So they have different integrations. One uses elliptical functions, the other one uses trigonometric functions, and we provide different models for the roto-translational intermediary. When we apply this concept of parallax elimination, all this stuff, we can just split the whole Hamiltonian, that is Kepler plus Euler, rotation plus orbit, and this is the coupling term that we split, that is V0. And on doing that, we have this term here, this is the V0, and this is the part that will destroy the integrability of the system. And on doing that, we are looking for, okay, this guy will be able to be enough perturbation to approach in this region the full Hamiltonian that we are analyzing. And this is going to be the reminder, that V type that we left. This is given by by this term here, and you have these relations. And we are leaving out the fast angles of the problem. Because the fast angles, we can consider here in this approach of this region of the phase space, they are not affecting the long-term dynamics of the problem. And under that, we can consider this theta is related to the orbital angular momentum, and it will become, when we leave it out, it will become constant. This delta will be related to the rotational angular momentum, and on doing that, we are also making this variable constant and null as well. So on doing that, we are also decreasing degrees of freedom to 2, just 2, and we can now have the system of equations of motion that we can integrate in terms of elliptic functions. We can do the same. This is the parallax elimination, just homological equations. It's very easy to find it in literature. And this is when we apply the elimination of the parallax to build the other model, we will get this generating function here. This is the equations that you have to use to return to original variables after you get the analytical solution in terms of trigonometric functions. And we have here the parallax Hamiltonian that we call, and we split, and from this term here, we split this term here. That is very similar to the previous one. But as you can see, the parallax elimination, you have here R cubed. When we apply the parallax elimination, we have R squared. That's the main difference. But this information is being carried here. The square that disappeared will be here in theta squared and this SK that we have here. On doing that, we have this is going to be the intermediary with elimination of the parallax. Now we have one roto-translational intermediary without elimination of the parallax and one with elimination of the parallax. And let's see, and this will produce these equations of motions here. Now we just take these parameters here to make some numerical experiments. These are two asteroids that are hypothetical ones. And we take this data from a previous paper from Ferr and Lara that is a good model to test the simulations, and we use this software Maple and this technique here. And when we propagate here all the models, we have here the rotation. I think yellow. I think it's not. Can you see yellow here? Yellow is the rotational motion and the orbital motion being propagated without coupling, free motion. So they are decoupled. In green, this lighter green is the triaxial model, but we just select A equal to B, and it needs to be reduced to the darker green. That is the axisymmetric model that we are comparing with. In blue, we have the model with with elimination of the parallax, but without returning to the original body, to the original variables using those transformation equations. And we have here in red is the model without elimination of the parallax. And in dark is the model with elimination of the parallax after you return it to the original variables using the generated function W1. How much time? Okay. The idea here, we consider a rigid body with almost no time, with just 1 degree of inclination. And we start to make experiments to see how precise when you start to tie this body. And the precision is lost on following this. But if you look at it's power of 10 to 5. So the precision that is lost is in fact very small. So both models, both intermediaries are able to approach the original models very well. And you can also make considerations about selecting different shapes, like a very oblate and almost spherical. And in both cases, the models will be like very spherical and very oblate case, and both models are following pretty well. And you can also select different eccentricities for the system and include, even when you modify the eccentricity, the model with elimination of the parallax, after you return to the original variables, is able to perfectly approach this model. Some precision starts to lose just when you tie it a little bit. Okay. I'm sorry, I will just make the conclusions, but okay. I'm sorry for the delay.
Thank you, speaker.